Here is the whole tower, fully assembled, glowing, finished. The neuron, the fold, the embeddings, attention, the block, the tokens. Every part of the machine now exists, and stamped across the front of it in angry red, one word. Untrained. It has never seen a single sentence. Every knob inside it is pure random noise. And here is exactly what I am going to hand you. You are going to watch one line fall on a graph and watch this dead pile of numbers learn to talk in lockstep right next to it. By the end, you will own the whole recipe for how a GPT is trained in 3 pieces, and it will feel almost insultingly simple. So watch what happens when a cursor reaches up, peels that red stamp off, and hits the glowing button that says train. The screen splits in two. On the left, a line poised at the very top of a graph, the highest it will ever be. On the right, the model's first attempt at language. And it is garbage. Not bad English, not broken English, pure static, a spray of random characters that means absolutely nothing. Now hold that promise in your head, because here is exactly what you are about to see. You are going to watch that line fall, and as it falls, that garbage on the right is going to sharpen, in lockstep, into letter soup, then into real words, then into something eerily close to English. You will see a computer learn to talk in a single falling line. And the best part? You already know how this works. Every idea you need, we built episodes ago. Today they finally all switch on at once. Let me prove that you already own this. Way back at the start of the season, one neuron rolled down one hill. We said learning is just 3 words, repeated. Predict, blame, nudge. The model guesses, we measure how wrong it was, we send that blame backward, and we nudge every knob a hair in the better direction. Roll and repeat. That loop is the entire engine of intelligence we built. Today, nothing about that loop changes. We just pointed at language. Here is the old ball, the same one from episode 0, rolling down the same simple valley. Predict, blame, nudge. Watch it find the bottom. Everything we do today is this ball in a far bigger valley. So we only need 3 new things. What game are we making the model play? How do we score its guesses? And what does it look like when you turn the crank not 3 times, but a few 100,000 times? Let's start with the game. The game is almost insultingly simple. We hand the model some text and cover the next word. Guess what comes next? That is the whole objective. Predict the next token. Every essay, every poem, every line of code GPT ever wrote, all of it falls out of relentlessly playing this one tiny game. The cat sat. Show it the cat, ask for the next token, and the right answer is sat. That is 1 round of the game. And now the quiet genius of the whole setup, the trick almost nobody explains. To play a guessing game, you need an answer key. Where does it come from? Here is the magic. The answer key is the exact same text, shifted left by 1. The input is the cat. The target is just the cat, slid over. After the comes cat. After the cat comes sat. The correct next token is always the one sitting right there in the data. The text is its own answer key. Sit with that for 1 second, because it is the reason any of this exists. There are no human labelers. Nobody sat in a room tagging billions of sentences. The data labels itself for free because the next word is always already there. This is called self-supervision, and it is the whole ballgame economically. It means there is no labeling bottleneck. You can pour in a chunk of the entire internet, and every single word in it is, automatically, one more practice question with the answer attached. So, we feed in a context. Now, what does the model actually hand back? It does not say one word. Watch the context flow up the tower we built last time, block by block, talk then think, riding the highway. At the very top sits one final layer we have not met yet. The output head. It takes the model's rich inner vector and projects it out into one score for every single token the model knows. 1 number per word in the entire vocabulary. And how big is that vocabulary? For GPT-2 and GPT-3, it is just over 50,000 tokens. So the output head spits out a row of 50,000 raw scores, called logits, 1 for every possible next word. High score means the model leans that way. Low score means probably not. But raw scores are messy. Some positive, some negative, none of them adding up to anything. We want a clean probability. We want to know, out of 100%, how much does the model bet on each word? So we run those scores through softmaxed, the same squashing function from the attention episode. It takes that messy row of 50,000 numbers and gently bends them into a clean probability distribution. Every value now sits between 0 and 1, and the whole thing sums to exactly 100%. On screen, it becomes a bar chart over the vocabulary. A tall bar for sat, a shorter one for dren, tiny slivers for everything else. For every position, a full opinion about every possible next word. And here is a detail that should genuinely surprise you. Thanks to the causal mask we built into attention, the model does not do this one word at a time. In a single forward pass, it predicts the next token after the and after the cat, and after every position in the chunk, all at once in parallel. One sentence is not one practice question. It is dozens of them, graded simultaneously. The shift by one trick plus the mask turns a paragraph into a whole exam answered in a single breath. Okay, the model has made its guess, a full distribution over every word. Now we need to score that guess, and that means meeting one idea with an intimidating name. Cross-entropy loss. It sounds like physics homework. It is not. Underneath the name is something simple enough to explain to a child, so let us take it slowly and turn it into one clear picture. Forget the name. Here is the only idea. Cross-entropy is a surprise meter. After the model guesses, we do one thing. We look up the probability it gave to the word that actually came next, the real answer. Then, we read off a single number. How shocked was the model by the truth? That is it. That is the loss. If reality matched what the model expected, barely a flinch. If reality blindsided it, the needle slams. Training is nothing more than turning that needle down over and over. Let me show you the meter swinging. The real next word was sat. Say the model bet 90% on sat, confident, and right. The needle barely twitches. The loss is about 0.1. Now say it only bet 10% on sat. It was caught off guard. The needle jumps, and the loss climbs to about 2.3. And if it had given sat almost no chance at all, the needle slams to the top. The more shocked by reality, the higher the loss. Now, where does that number come from? It is one of the cleanest formulas in all of machine learning. The loss is just the negative log of the probability the model gave to the correct word. That is the whole thing. Negative log p. And watch why log and not something simpler. As the model's confidence in the truth slides toward 0, this curve does not just go up. It explodes, screaming off to infinity. A model that thought the real answer was nearly impossible gets punished brutally, exactly as it should be. And here is the part that finally kills the scary name. The textbook writes cross-entropy as a giant sum over all 50,000 words. It looks terrifying, but watch what happens. The true answer is one word. So the target is what we call one hot. One word gets 100%. Every other word gets a flat 0. Now watch the sum. Every term gets multiplied by its target, and all those zeros annihilate their terms. The whole monstrous sum collapses, term by term, down to a single survivor. Negative log of the probability of the one true word. Let that land. The terrifying cross-entropy sum is, in the end, just negative log p of the right answer. The surprise meter and the formula are the same thing. There is one honest footnote, and it is beautiful. This number is measured in bits, and it literally counts how many yes or no questions you would waste describing the real text using the model's guesses. Minimizing surprise is the same as building the most efficient possible code for the language. Compressing it well is understanding it, but the meter is all you need to remember. We are over the hard part. Breathe. So now we have one number for one guess. We do that for every position in the chunk, average them all together, and out pops a single scalar. Today's wrongness. One honest number that says, across all those guesses, how surprised was the model, on average, by reality. That number is everything now. It is the only thing standing between a pile of random weights and something that can write code. The whole field watches it like a heart monitor. Now we close the loop. We have a prediction, and we have a number for how wrong it was. Predict, done. Blame, next. The loop ring spins. Backprop sends that blame racing backward down the tower, exactly the chain rule from episode 0, asking every single knob one question. If I nudge you a hair, does the surprise go up or down, and by how much? And remember the residual highway from last episode? This is where it earns its keep. The blame drives all the way to the very first floor, undimmed. Then nudge. Every knob takes one tiny step in the direction that lowers the surprise. And there is our old friend, the ball, taking exactly one step downhill on the loss landscape. Predict, blame, nudge. The ring completes one full turn. The step counter ticks over to 1. One honest footnote: in practice, a smarter step picker called Adam tunes how big each step should be, faster here, gentler there. But in spirit, it is the same ball, rolling down the same hill. Nothing about the loop changed. And that is one training step. One turn of the ring. Now here is the whole secret of how you build a GPT in one sentence. You do not do anything clever next. You just do that again. New chunk of text, predict, blame, nudge. And again. And again. The step counter starts climbing. 1,000. 50,000. 200,000. We are about to turn this crank a few 100,000 times and watch the line fall. This is the payoff the whole season has been driving toward. Back to our split screen. On the left, the loss curve. On the right, the model's live writing. And down at the bottom, a terminal, streaming the training log the way it really looks. At step 0, before a single nudge, look at the loss. It is pinned near the top at about 10.8. And that number is not random. It is the most beautiful sanity check in the field. A brand new model with random weights has no idea which word comes next. So it spreads its bet evenly across all 50,000 odd words. It is, quite literally, rolling a 50,000-sided die at every single position. And the surprise of guessing right on a fair die that big works out to about 10.8. Run it backward, and that is a perplexity of 50,000. Perplexity just means the effective number of choices the model feels torn between. At birth, it is torn between every word it knows. It is maximally, perfectly confused. That is our starting line. Now press play, and do not look away from the right pane. Step 500, and the loss has already dropped. The garbage on the right shudders and resolves into letter soup, clumps of vowels and consonants that almost look like they want to be words. The model has learned, dimly, that letters cluster. It does not know any words yet, but it has stopped screaming static. The line on the left ticks down, jagged, noisy, but trending unmistakably down. And notice the line is not a smooth slide, it jitters. Up a little, down more, up, down, down. That jaggedness is honest. Every step sees a different chunk of text, so every step is a slightly different hill. What matters is not any single step. It is the trend, the relentless downward drag underneath the noise. Keep watching the right side. Step 5,000. The letter soup is condensing. Real words are starting to crystallize out of the fog. The, and, of, he said. Step 50,000. The loss has fallen from about 10.8 down toward 3, and the right pane is no longer soup. It is sentences. Clumsy, sometimes nonsensical, grammatically shaky sentences, but unmistakably English. Subject-spined verbs. Quotes open and close. The model that was rolling a 50,000-sided die is now, in effect, rolling something closer to a 20-sided one. From 50,000 choices down to a rough handful. Watch the loss curve and the words at the same time. They are the same event. The line falling is the model learning to talk. And look at the shape of the fall. It plunges fast at the start, the easy lessons, then bends into a long, slow, grinding tail. The first cheap wins, letters cluster, common words exist, come almost for free. The last gains, real grammar, facts, a sense of style, cost enormously more. Most of the money and most of the months go into that flat tail, squeezing the last fraction of surprise out of the truth. This is the heart monitor of the entire AI industry, ticking down one fraction at a time. Let me make that grind real. To train the famous big GPT, they poured in around 300 billion tokens of text. By one estimate, to read that much, a human reading nonstop, day and night, never sleeping, would need over 2,600 years. 2,600 years of reading, crammed into a single training run, scored, one surprise at a time, against this one falling number. And turning that crank is the single most expensive act in all of software. That one run is estimated to have taken so much computation that a single graphics card, working alone, would have needed something like 350 years to finish it. They did it in about a month by running thousands of chips in parallel, at an estimated cost reaching into the millions of dollars. Millions of dollars spent to push one number down a graph, which tells you exactly why everyone stares at that line. Nobody watches a model get smart. There is nothing to watch. You watch this one scalar tick down, and you pray it keeps falling. If it stalls, or worse, swings upward and diverges, every one of those millions of dollars and all those hundreds of card years buy you nothing but expensive noise. The loss curve is the heart monitor, and a flat line means the patient is dead. One number decides whether you funded a genius or a very costly random number generator. One honest warning before we celebrate, because you should never be fooled by this. A falling loss does not mean the model is right or wise or true. It only means one thing. The model is less surprised by this particular text. So whatever lives in that text, every bias, every error, every confident falsehood, the loss faithfully teaches the model to predict it too. Lower surprise is not the same as truth. The model becomes an exquisite mirror of its data, flaws, and all. Hold that thought. It opens a whole other story, much later. But step back, because what you just watched is genuinely one of the strangest facts in science. Grammar, facts, translation, arithmetic, a sense of humor, the ability to write working code. None of it was taught directly. Nobody wrote a grammar lesson or a coding tutorial into this thing. All of it fell out as a side effect of one dumb little game played a few 100 trillion times. Be less surprised by the next word. That is the entire instruction. Everything else is emergent. So let me close the loop I opened and hand you the whole thing in one breath. I promised you would watch a computer learn to talk in one falling line, and you did. Here is how. The game, predict the next token with the text as its own free answer key. The score, cross-entropy, just a surprise meter reading how shocked the model was by the truth. The loop, predict, blame, nudge, the exact same ball from episode 0, rolling down a far bigger hill. Turn that crank a few 100,000 times, and the line falls. And the kicker is the simplicity of it. We did not invent a single new idea today. We took the loop you have owned since the very first episode, gave it a game and an answer key that comes for free, and pointed it at the whole internet. The wow was never the cleverness. It with that one blind, mechanical surprise meter turned down a few 100,000 times is enough to teach a pile of random numbers to write. Learning, it turns out, is just refusing to stay surprised. The loss has flattened. The line has reached its long, low floor. And on the right, the model is humming, confident, fluent. It did it. But now look closely at what it is actually producing at every step. Not a sentence. This. A glowing bar chart. A clean, confident probability spread over the vocabulary. After your prompt, it says, maybe this word, probably that one, a small chance of this other one. And that is the strange, anticlimactic truth of a trained model. For all that money, all those years of reading, all that falling, what you have built is not a writer. It is a next token probability machine. It does not output words. It outputs odds. A fully trained GPT, faced with your prompt, just hands you this. A chart of how likely every possible next word is. That is all it can do. So we are left with one last maddening gap. The loss is dropping. The machine is trained, but it speaks only in probabilities and odds over a vocabulary. And nobody talks in odds. So how on earth do you turn this glowing bar chart, this distribution over 50,000 words, into an actual flowing sentence, one word chosen after another, until a thought is complete? That choice, it turns out, is its own art. And it is where we go next.